We're going to get in the right page here. So the first thing is today's recitation is optional, and anybody can go. You could, if you want help with the homework, you can come back and get your homework, and then go to that. It's at 3 p.m. in the same PSA 111, is it? Is that where your recitation is? Everyone's, yeah. So go 3 p.m. 111. That's optional for anyone to go to get help to finish this homework or ask any questions that you want. Okay? And then Monday we'll have quiz. Next homework will be Wednesday. So kind of normal weekend, even though we have a break. We'll do quiz Monday, and then homework Wednesday. And then in terms of exams, mastery exam. If you still have not taken, if you did not pass number 2, and you need to take number 3, you can come Monday or Tuesday in office hours, 2:45 to 4:15, or by appointment if that doesn't work for you. So there's still a handful of you left that have not passed the mastery. If you don't come and take it a third time, you're going to get a 0. Okay, you're just going to get a 0. All right, exam 3 is a week from tonight. It's Wednesday. It covers everything since exam 2, and that was a long time ago because we had the mastery exam in the middle, so that it kind of extended the time since we had exam 2. So if you go to, for exam 3, if you go to exam prep, I made a folder here, exam 3, Wednesday, December 3. This time I went ahead and put the quizzes there, okay? Instead of in homework and quiz solutions, I just went ahead and put the quizzes in the exam prep area in the folder called exam 3. So here's all the ones you took, but then I have all of last year's. And in previous semesters, they took quizzes in recitation, and they were longer. So there's going to be lots of good practice in there. There'll be some overlap, a little bit of overlap, but there'll be lots of new questions you have not seen before, all great for studying for the exam. I highly recommend that you work on them without looking at the solutions. Work on them without looking at the solutions. Work on them with a friend without looking at the solutions. Get help before you look at the solutions. Looking at the solutions before you've really gone through that mental thinking process and took it to the end is going to make that a less valuable experience. If you're just sitting there looking at the solutions like, oh yeah, I get that, I get that, I get that. And on the test, you'll be like, I don't get that. Okay? So make sure you really put yourself through that thought process of trying to do it like it was a test question. And then even get help from other people before you look at the solutions, okay? I highly recommend that. So lots of good practice along with the quizzes that we took. All right, so then these are all the ones that you guys took in lecture, okay? And then also there's also an outline. So in that folder, also a review outline for exam 3. There's nothing on the exam that's not mentioned, talked about in that review outline. Okay, so you got the review outline. You've got our quizzes and solutions. You've got a previous semester longer quizzes and solutions. So, and then you have a week to get ready. Many of you are asking, how can I improve my grade in the course? Focus on exam 3. Get started early. Okay, next thing. We talked about the mastery exam, exam 3. So the final exam then is the following Tuesday. It's 2 weeks from yesterday. So, and you'll see when you look at the review sheet, again, if you go to exam prep, you see I posted a final exam review sheet. You'll see a heavy emphasis on the second half of the course, exam 2, 3, and after. Okay, so that's why you should focus your attention on exam 3 now. And then you'll have 5 or 6, you'll have 6 days to then kind of do your overview studying for the whole final. Okay? Questions on exams coming up or other announcements? Oh, when is the final exam? The final exam is when and where? So on the announcements, I have all this information, including location and time. Tuesday, December 9th, 7 p.m., PSF 166. PSF is just west of Goldwater. You know where Goldwater building is in the engineering library? Go a little bit west. That's where PSF is, 166. Okay, those are All the announcements I can think of. Anybody have a question? Cool. All right, this is a really important day because we are coming to the culmination of the course, the fundamental theorem of calculus. About 80% of what we've done so far has been all about coming to develop and understand the fundamental theorem of calculus. So, in the first half of the course, we looked at the situation. We have what and we want what. Do you remember? This is the first half of the course. We know how much we have or how fast it's changing in the first half of the course. How fast it's changing. We were given a rate function. This is the whole first month and a half of the class. Given the rate of change, we wanted to know how much of it we have, right? You know how fast something is changing. You want to know how much of it you have. That's what we started with. Okay, so here's an example, and we kind of looked at this example last time. Using the exact rate of change of elevation, function r. So we have an elevation situation. The left graph is giving the rate of change of elevation, and that function is capital R. Write a function f that gives the exact accumulation of elevation starting from c miles to x miles from the border. Everyone do it. You should be able to do it if you've learned something in this course. So, suppose we're going to talk about starting from anywhere here, c, to any variable stopping point x, and we want to know what is the total accumulation of elevation, or the change in elevation from c to x, given the rate function r. An exact amount of accumulation starting at c, ending at x. Quiz yourself. Everyone in 30 seconds, see if you can get it. Okay, did you get it? It should have been this. How many people got it? Yay! Excellent. Okay, so, and was this an open form or closed form? Open form. It reflects the process. So what process did it reflect? So accumulation, what's the idea of accumulation, and how does this expression reflect that? Accumulation occurs. And if we want a total amount of accumulation, what do we do?
Add up interval input multiplied by the rate.
Okay, right. So we're going to accumulate. Accumulation is a sum. It's a sum. And how do we see the sum idea in this expression? No, how do we see the sum? Just sum. German S. It's German S, right? It's the sum of what? Lots of little bits of change. Each bit is computed by k delta x. As we see k delta x there is r dt, right? A value of r times a little itty-bitty change in x, which is a little itty-bitty change in accumulation. We sum all those up, and we get a total amount of accumulation. Okay, so this is open form, reflecting this process of accumulation occurs bit by bit, and then we sum up the bits. And when you see an integral, this is what should be going through your mind, this idea, okay? But we never found a closed form. We just turned the tables and started talking about the other question, and we never found the closed form accumulation function. We just stopped with this open form. We said, we need GC to graph this, or we need technology to find us output values of this. We don't have a closed form, meaning a familiar function that can just spit out amounts of accumulation easily. Okay? So, ask another question, example. If E is an elevation function, how can F also be written in terms of E? So if F, how can we also write F in terms of E? So same thing, if I'm looking at the amount of accumulation starting C miles from the border to whatever, X miles from the border, variable, right? How can you use E to write the function F? If E is the true elevation from the border function. Okay? Everyone should be able to write that down. How could you use e to rewrite this function f? Tell the person next to you. What would it be? Is it the integral? The integral from c to x, e of t dt. Is that what it is? No. What would it be? E of x minus e of c. It'd be the final elevation minus the initial elevation. Okay, so then we spent all this time on the mastery exam learning what's called derivatives. Okay, the mastery exam enables us to find closed form rate from accumulation. So given an accumulation function, all those rules are giving us a closed form rate of change function. In other words, r is the derivative of e. You see that? So this, now that we have all these closed form rules for getting rate from accumulation, that's the key to this missing piece of our puzzle, finding closed form accumulation functions. So we've got these rules that get us rate from accumulation in closed form, and we're going to use that knowledge now to finish the puzzle here of getting closed form accumulation functions. Super important. We're putting everything together here. Any questions before we go on to the next slide? Okay, so closed form accumulation function. So we said this, that the accumulation starting at c, ending at x, would be the integral of rt dt, or it'd be just the final amount of accumulation minus the initial amount, right? That's what we just said on the previous screen. So suppose we have f of x equals x squared, and that's an accumulation function, and from the mastery test we learned that its rate of change function is, they said in chorus, 2x. So now suppose you have this open form accumulation function, starting accumulating at 3 to x of 2t dt. What does that equal? What does that equal? Just follow that up there. So we know that the accumulation in open form equals f of x minus f of c. So what would it be? F of x minus f of 3, right? And what is f of x? X squared. What's f of 3? 9. 3 squared. So what did we just find? What's x squared minus 9? What kind of function is that? That's a closed form. We can just plug in values of x and it spits out amounts of accumulation. So that's the closed form representation of 3 to the x, 2t dt. Well, how was that made possible? It's made possible by the fact that we knew that 2x was the rate of change of x squared. So if we have the accumulation of a function that's accumulating at a rate 2t, we know that x squared is its accumulation function. And so then, therefore, this particular one will be x squared minus 3 squared. Okay, practice again. So f of x equals e to the x cubed. Everyone write down what's the rate function for e to the x cubed. We're all masters, or most of us anyway. We're masters. We just do this in our sleep, right? What is it? E to the x cubed times 3x squared. So if you have the open form accumulation function starting at -1 to x of 3t squared e to the t cubed, what is that the same as? You can rewrite it as f of x minus f of -1. F of x is 3x e to the x cubed, and f of -1 is e to the -1. So -1 cubed is -1. So this is e to the x cubed minus e to the -1. which if we wanted to get amounts of accumulation, you know, starting at -1 up to x, what are you going to use? Are you going to take the time to put that in graphing calculator and get the values that you want? Or that's a lot more convenient, right? Because it just spits out outputs, accumulation in closed form, knowing that this was our rate of change function. Okay, so let's test it. Let's make sure that we are doing it right. So if I go to, I'm graphing here. Am I graphing accumulation or rate? Can you see it? No, you can see it. Does it show up enough to see it in the back? You see it? Cool. All right. I'm graphing in gray. Am I graphing the accumulation function or the rate function? Accumulation in open form or closed form? That's open form, right? So that's our reflecting the process. And we found that this was the closed form representation. So when I turn that graph on, is this what we found for the closed form? If I turn it on, what should happen? Should be exact same graph, and it is. Okay? So this reflects the process. It reflects the rate of change from which it came from. This, we can't see the rate explicitly in there, but it will just crank out values, rapid fire, of amounts of accumulation. Okay. Go. Piece of cake, right? Rate of change is 4 cosine 4x. So now you have an open form accumulation function. The integral from pi over 3 to x, 4 cosine 4t dt. What makes it possible for us to write this in closed form? The fact that we know, see, when you took that derivative, you didn't just get the rate of change function, you also found out something else. What else did you find out besides that 4 cosine 4x is the rate of change of sine 4x? You found out something else. What else did you find out? What's that? Be specific. Be specific. What else did we learn when we took that derivative and we got that the rate of change of sine 4x is 4 cosine 4x? What did we also learn when we did that?
The accumulation function for 4 cosine 4x and sine 4x.
That's it. The accumulation function for 4 cosine 4x is sine 4x. So now we want the accumulation function for a function whose rate is 4 cosine 4t. So what is it? It's going to be sine of 4x minus, or f of x minus pi over 3. Okay, so by learning all those derivative mastery rules, you didn't learn just to find rate of change functions, you also learned how to find closed form accumulation functions. Every time you found a rate of change function, you found out an accumulation function given a rate of change function. Okay. Does this make sense? This is really powerful. This is huge. This is where we've been heading to all semester. Okay, so in the mastery test, we didn't do any simplification, but we want to simplify this one. So I'm going to give you a hint. What does A over radical A equal? Does anybody know? Or can you figure it out? A over radical A. So So we could do radical A over radical A. And we would get, isn't this in the denominator just, what is this? That's just A. Therefore it equals radical A. Okay, that's a hint. So when after you take the rate of change, use this idea to simplify it. Go. Next semester, sitting and not writing is not going to be allowed in my class. So, I hate it. I love you, but I hate it. Okay, so hopefully most of you have arrived there. Did you get that? Or are you close? Do you see that it is that? Based on this principle here. Squinting your eyes because you weren't writing. Okay, are we good? Okay. Those who worked on it, see it. So that's our rate of change function. So that being the case, given this rate of change function, RG, write its accumulation function. If the accumulation starts at x equals -2, and write that in two ways, in open form and in closed form. Go. When an accumulation function starting accumulating at -2, I want you to write it in an open form representation and a closed form representation. Yeah.
I didn't write it down, but it is in my head. I got a 2 as a coefficient for that. Where does that go? Because it's x squared.
Chain rule. 2x. 1/2 radical. The derivative of radical is 1/2. Okay, you should have gotten these two right here. Check your answer. So, based on the rate that we found, it would be the integral from -2 to x of that rate dt. And then, that's open form. Your closed form should be that right there. How are we doing? Are we good? Is that what you got? Question? Or scratch? Yeah.
So instead of RTDT, do we get like negative x?
Say it again.
Or that instead of RTDT, you don't write the RG of x. The rate function we
Well,
derived.
no, but it's graphing calculator, right? So I've defined Rx in the previous line, so I can just use R RT, right?
So it's e to the negative x squared.
Right.
The function at -2
Yeah.
with the -2 by the negative.
No, but it's not negative x squared. It's the opposite of x squared. Because if you do power first by order of operations, you do the power first and then you do multiplication. Okay, so this is important. Order of operations, what comes first, the negative or the square? Exponents come first. So you're going to square x, and then after you square x, you're going to take the opposite because you're multiplying by -1. Okay? So that's why it's e to the -4, not e to the 4. Are we good? So let's check it. So I'm going to graph the... that's graphing the open form there. And then, if I graph closed form, it should land right on it. Nothing happened, right? Because it's the same graph. Okay? So when I turn on that graph, these are the same. So we have a closed form representation for that open form accumulation function. So here's this accumulation function. So how do we see in the graph, where do we see showing up in the graph the fact that we are starting accumulating at -2?
It goes above the x-axis.
What's that?
It goes above the x-axis.
It goes above. It's because it goes above the x-axis. Is that the reason why we're starting at -2?
Oh no.
The rate function.
Can't have negative value for accumulation.
You can't have a negative value for accumulation. Is that true?
You just chose it.
What's that? So I chose to start accumulating -2, and then this is the graph we got for the accumulation function. How is it seen in the graph that we're starting accumulating at -2?
Point of inflection.
Point of inflection. Sam. -2 is a 0. -2 is a 0. Accumulation can be positive, it can be negative, it can be increasing, it can be decreasing. But starting accumulating at -2 means if we plug -2 into that function, what should we get? 0 amount of accumulation. So it could go down from there. It could be negative from there, right? But the fact that it has a root at -2. So then, that brings up the question, what will happen? So what about this accumulation function? What will happen to the graph if we do an accumulation function, we do start at -1? What if we start accumulating at -1? What will the new accumulation function be like? So, so what will happen? What will we know at -1? At -1, what will be true? We'll have a 0. Okay, so are you imagining this? This would be the new accumulation function. This shall be our conjecture. We don't know for sure, but does that start accumulating at -1? Or is that 0 at -1? So this is our conjecture. We're not saying it's right or wrong. We're gonna discuss it. So this is our conjecture for -1 to x RT dt. Okay? What do the two accumulation functions have in common? So not the graphs, but looking at accumulating the original one we had starting at -2, and the new one we have starting at -1. What's the same about those two accumulation functions? They have the same what? Rate of change, right? They have the same rate of change function. So let's test that. Let's look, for instance, here at, how about negative 0.5. So here's our conjecture for that one. Here's our original accumulation function. How is the rate of change represented visually on these graphs? How's the rate of change represented visually? Relative size of the change in y to the change in x, right? Derivative. So, at negative 0.5, same or different? Same relative size of... Doesn't this one look greater than this one? Let's do a better example. How about 0? How about the rate of change of our conjecture and the rate of change of our original accumulation function? What's the rate of change of our 0? What about our conjecture? A significant positive result. So, how about our conjecture? They have the same rate of change function. Yeah, we got the negative 1 part right where it's going to start at 0. But these have different rate functions. So this can't be the rate of change of negative 1 to x. So what we need is, we need a function that, yes, it has a 0 at negative 1, but it has the same rate function as this one. So how can we get one that has the same rate function as our purple one, starting at negative 2, but has a 0 at negative 1? Talk to the person next to you. So I'm going to turn it on. I'm going to turn it on. What am I going to see? Do you have an image of what you're going to see? See if you're right. Here we go. Does it have the same rate function? Does it have the same rate of change profile across all x's as our original? Yeah, if you take a vertical line on any x value, the relative size of the change in y to the change in x is the same, or the slope is the same. Okay? Does it start at negative 1? Yeah. It has a 0 at negative 1. Okay, so let's do this. I want you to write out the open form for the new one. Write out the open form, closed form. We got the open form. That's open form. Write out the closed form for this new, the blue graph, which is the same rate, but starting at negative 1. What will it be? What should I put first? Closed form for this function would be square root e to the negative x squared minus square root e to the negative 1. So now so those should be the same. So if I turn that off, it's blue. If I turn it and make it black, then it's the same. So now look at the closed form for our original accumulation function starting at negative 2, and the new one, the closed form for the new one here starting at negative 1. I'll copy and put them next to each other up here. So I'm going to put it again up here. How does a comparison of the closed form equations, comparing those two, how is that consistent with what we're seeing in the graphs? Okay, so how is comparing those closed form equations consistent with what we saw when we compared the two graphs? Go, talk about it. Are you going to answer it? Yeah. I'll let you answer it after people talk. How are the equations consistent with what we're seeing for the two accumulation functions? Well, I'm giving it away here, but there we go. Okay. So, Chance wants to answer. So, how do we see what we saw in the graphs now in the equations? Go ahead.
So, if you're taking an integral from c to x, then because of the form, 1/2 of like all the terms with x don't use c, and all the terms with c don't use x. So no matter like where your c is, you're gonna have a part that has the x in it, the part that doesn't. So you're just gonna have a different constant for whatever your c is. It's the same function, different constant.
Okay, so you did. All right, so you talked about it, but what about the graphs?
Constant just moves it up and down. It's y value.
Okay, so that's what I was getting at. So what we're seeing in the graphs, right? So what are those? They're just constants. So what happens when you subtract or add a constant to in a function? What kind of shift do you get? An up or down shift, right? So if you have a function and you add or subtract from its output, you're just going to get it's going to be shifted up or down. And so that's exactly what we're seeing here with these two accumulation graphs. When you shift an accumulation graph up or down, what happens to its rate? What happens to its rate profile? Nothing. All the rates of change stay the same. And so that's how we get many accumulation functions from the same rate function. Okay? Many accumulation depends on where we're starting, and depending on where we're starting accumulating from is going to affect how high up or down the accumulation function is. But won't affect the rate. So here I've got it set up so that now I've got a variable, okay? So if I change A, if I change the starting value, what will you see with the graphs? Yeah, so all these accumulation functions have the same rate of change. It's just starting, you're just starting accumulating from a different place, so you get a 0 at a different place. But they all have the same rate. And so in order for that to happen, it's got to be different vertical shifts of the same accumulation graph. So here is negative 0.4. So you see a 0 at 0.4. Here's 1.2. So this is A equals 1.2. So that's giving us a 0 accumulation starting at 1.2. And then notice accumulation starts negative from there if you increase x. Perfectly fine. Okay, so if that only partly made sense, watch the video. That's a super important conversation right there. Hope that made sense. Okay, so let's go back to the... So what we're talking about is, now what we're talking about is what's called antiderivatives. Antiderivatives. Knowing all our derivative rules then allows us to know antiderivatives, which would be like, okay, can I have your attention, please? If you want, yeah, if you're whispering about math, I'm great with that. But I feel like it was more than that. Okay, so antiderivative then would be, let's talk about it. Here we go. If g is the derivative of f, g is f's rate of change function, then f is called an antiderivative of g. Okay, so we did lots of these, right? We said we learned all these rules in the mastery test. Given a closed form accumulation function, we've learned all these rules to find closed form rates of change function, and those were derivatives, right? Derivatives. Well, now, f is the antiderivative of this df dx, okay? So every accumulation function is an antiderivative of its rate of change function. Should make sense, right? Every accumulation function, the one f over there, is an antiderivative of its rate of change function. Okay? Given a rate of change function, so given an accumulation function, how many rate of change functions does that accumulation function have? One. There's only, if it's accumulating in a certain profile, there's only one rate of change function. Given a rate of change function, how many accumulation functions could you have for that rate of change function? Many. All right, so every rate of change function has more than one antiderivative. So every function only has one derivative, but every function has more than one antiderivative. And that should make sense, thinking about rate of change and accumulation, what we just saw. Okay, so every rate of change function has more than one antiderivative. So here's the rate of change function, 4x cubed. Can you write the closed form version of this open form version of the accumulation function? So can you write the closed form version? Should be able to, right? Because we're saying this, how does this relate to the open form? How does that right there relate to the closed form accumulation function? What is this related to the closed form accumulation function? It's derivative, it's rate of change. So what function has that as its derivative? X to the fourth. Therefore, closed form is x to the fourth minus 1 to the fourth, or 1. X to the fourth minus 1. That's it. Okay? What about this one? So, what accumulation function has 4t cubed as its derivative? X to the fourth. Therefore, a closed form accumulation for this one is? Fourth minus? And what is that? 625? Okay, so if this is an antiderivative of, how can we check to make sure that this is a valid antiderivative of 4x cubed? Take the derivative. And we get derivative of x to the fourth is 4x cubed minus 0. How about this one? Okay, so this is a valid antiderivative of 4x cubed because its derivative is 4x cubed. Same with this one. Here's another valid antiderivative. of 4x cubed. Why? Because its derivative is 4x cubed. Closed form. X to the fourth minus pi to the fourth. Check it. So therefore, the rate of change of this must be that. Is it? 4x cubed. Okay, so the improper integral, if you don't see anything there, it's called the improper integral. Doesn't have any limits of integration. What does that mean? That's all antiderivatives of 4x cubed, every single one. So you imagine just this is an a down here. Okay? Imagine that this is a. Okay, so it would be x to the fourth minus a to the fourth, which we rewrite that minus a to the fourth is just some constant. Okay? So in there, again, all the different vertical shifts of the same accumulation function all have the same rate, in this case 4x cubed.